We're trying to distance something. Okay, good. The body will progress. Okay, so thank you. So we'll just do carry on martingales, basically some key results. That's how we're approaching this. Okay, so does anybody know about this? This was maximal inequality. This was some martingales. So we're given a martingale. Let's call this M of n, non-negative, I guess. So we define this maximal process. So Mn star is equal to just the maximal process for a submartingale. The result is, what we see for Markov process. So this, of course, is just for Markov, right? Markov inequality. The point is for martingale system. So you get tighter inequality for some martingales, for non-negative submartingales. And if Mn is a martingale, then absolute value of Mn is a submartingale. So to that extent, it's also saying something about martingales. Okay. So it's already interesting, right? You begin to get tight results. So we'll do this today. We do this as one result. Second result, which is actually more interesting nowadays, is what's called Willis inequality. And that's that if you have a super martingale, and then you ask yourself, okay, what's the problem? So super non-negative martingale, then you know that, okay, you actually know that Mn is going to converge to M infinity, right? It's a non-negative super martingale. Martingale convergence theorem. Because it's L1 bounded. So M infinity exists. But then we look at M star infinity. This will have a limit. So M star, this just means, so this is giving me lambda. And that's going to be less than equal to E of M0. So this is, saying that the probability that there exists an n such that Mn is greater than that. That's what this supremum means. We're bounding that.
Non-negative submarine.
Non-negative. Non-negative. This is going to be for Willis for supermarket. You can't have both. So I'm just summarizing something we're going to do before we start. And this is very nice stuff because at least in learning theory, for example, we have these stopping rules, adaptive stopping rules. And this is saying that so we need concentration inequality basically, anytime concentration inequality. Not just that the random variable at time n is close to something with large probability, but it's always close to something. It never goes outside a tube, so to speak. So then there exists a time when it goes outside the tube. That's bounded by these kind of properties. So it's enormously useful. Something which has not been exploited so well in the past. It's a very new thing and it's being done in learning. So Willis inequalities are the key. And then we are going to we come back and do groups. LP inequality. N star P. In the P norm, it is growing, but they're saying it's not going very fast. This is again for some martingale. So P is greater than 1. This is for some martingale. So these are some martingales. So this is again a fascinating result, which is saying that when you have a martingale or some martingale, the supremum is not going very fast compared to the last entry. And then I guess we should have time, so we'll do L2 martingales. Maybe 2 minutes. Decomposition. It's good to show this that every adapted process can be written as a martingale plus a pre-visible process. It's kind of an obvious thing to say in discrete setting, but enormously powerful in continuous setting, which we will not do. But nonetheless, it's good to see this. But at least it just gives clarity to the fact that if I give you any sequence of random variables which are adapted, there's a very obvious martingale that comes with it. You get to see that at least. And then all these martingale results are available. One good area for martingales, just to keep in mind, so you're familiar with all this kind of steepest descent gradient based method, right? When we do optimization. So you go like this and you come to that point. So a popular method, and I guess that's also true now in machine learning, is learning and all is that noisy gradient method, stochastic gradient method. So now when you're doing gradient, you have some noise attached to it. You basically what you do is you change the step size slowly, you reduce it so that the noise kind of vanishes and you still kind of should right point. So to show that the noise that you're kind of collecting as you go along is not contributing very much, all of that again boils to showing that the noise is basically a martingale sequence, and typically L2 martingale sequence. Second moments exist. So then whatever we're going to discuss here, what L2 martingales, that becomes very useful, very commonly used. This is kind of stochastic approximation theory. So martingale is kind of the tool to kind of play around with anything in involving probability nowadays. There's no way around it. Okay, so that's the agenda for today. Let's do Maxwell inequality. Do a more detailed indicator. Mn now is a sub-martingale and it's non-negative. We'll show these things. That's more than what we did. Okay, so first we'll define stopping time. Tau is equal to infimum n, such that Mn is greater than lambda. First time is lambda, that's stopping time. You can convince yourself that probability that Mn star greater than lambda is equal to probability that tau is less than equal to n. Right, we're seeing the same thing. The same events, same probabilities. And now on the set tau is equal to m, right? We have this probability that tau is equal to m is less than equal to. So indicated that tau is less than equal to m is less than equal to m of tau, right? It's non-negative and on lambda into indicator that. Because the M1 tau is bigger than lambda when you stop. Right? And this is actually M of n. Right? And that tells you okay, probability. So it's actually quite simple. Value of M of n. Okay, how do you suggest we proceed? What do we want to show? We want to show that E of M of n, right? Some. Huh? Some n from. Okay. Before we sum, there's one thing we need to do. We don't like this small length. We want to have small length.
If less than equals to expression of
Hmm?
it is less than equals to expression of
Because the supermarket, because the submarket. Exactly. And this is, this is an event which is in FM. And we know that we know this property of submarket, right? E of M of n given Fm is greater than equal to M of n. Okay. So that means this guy on Fm integrates less than Mn. We get a bound as well. That's the main thing. And now we do what you said. Now we sum it. So this over all n equal to 0 to n. So you get okay, probability that tau is the same to n. Equal to probability and then star is greater than lambda. That's less than equal to E of and then star is greater than lambda. And that's okay. Now let's do, so now we shift here to super martingales. Because the tools are similar, that's why I've combined this. So that's now we do Miller's inequality for super martingales. You want to see Miller's statement? I just write it down again. Let me just write it down again. So super martingale, I guess what we're saying is probability that m star infinity greater than lambda is less than equal to E of m0 m0. The other way around. So it's a super martingale, so we know that E of m0 is greater than equal to E of m n min tau. Tau is again defined as first time you cross lambda. Because the super martingale is greater than equal. Okay. Okay, so that tells you that if Everything is non-negative also. This is non-negative supermarket. It's non-negative supermarket. Yes. So, only thing is, we not assume now that tau has to be finite. That is not assumed. This is okay. Very nice. No intuition. But to right? U of m tau indicator around this infinity plus u of. And we also know that N converges to M infinity. And L1 boundary, that's martingale, super martingale. All that is at the period earlier. This is E of M infinity. Can anyone see how the proof will proceed? So we have this, right? E of M0 greater than equal to this. And we want to show that it's probably that M star infinity is
The right hand, the last term was question was the expression of M0 indicator I indicator tau equals C.
what's that?
The last term is this time equal to
Quite straightforward from here. Last term, you're right. You think a little bit more. What can you say about M tau? Huh? At least lambda, right? So we're done this. You can actually ignore the last term.
Yeah.
That's exactly the thing that you wanted. That's exactly the same. So you get the bound. Such a cheaply obtained bound and such powerful. You can't. It's amazing how much stuff we can do just with this probability, with this inequality. So I'm not going to prove law of large numbers in a kind of elaborate sort of way that normally one proves strong law of large numbers, but just the first known condition. Those things you should read up on your own. David Williams does a good job. All the books talk about this. I'll just cover a simple proof of it using reverse martingales. Maybe in the next lecture soon. So you get to see the one proof of it, and it's pretty like 1 or 2 lines kind of proof. But you'll see that earlier you're taking 5 pages, now you're taking 2 lines to do the same thing. Okay, so now we have to prove this thing here. Now let's come back to so Billions was of course done by Billion. And I guess I forget the story now, but somehow it was discovered recently. It's not known for long. It's Billion inequality. But it's worth reading about. Maybe I'll read up at some point. You can also read about it. But all the other stuff, including coming up with Martingale's topic time theorem, Martingale convergence theorem, maximum inequality now proves LP inequality were all done by DL. He did everything himself. And you could say that because he developed the whole thing, it made it easier for people to use it. and that maybe also contributed to its popularity. You just do a few things and nobody else takes it up, and you keep giving it to other tools. We're going to show. Assume ML is a is ML. Yeah. MN is all non-negative, MN star is the maximum. Let's keep it expecting that.
The implicit expression and integration
What's that?
integration.
It's all non-negative. You can also you can answer that as well.
Like shouldn't that be indicator of x greater than equal to n star?
Yeah, that's what I'm thinking. Kuch gabad to hai.
Yeah, like x is great.
Yeah, it should be X here, I guess. Yeah.
X less than n star.
Yeah.
Sure. Yeah. Right. Now I guess then I might as well. Yeah. Then I guess I might as well take the expectation inside. And now I observe that okay, X into probability that Mn star is into X for all X at this bound is less than equal to E of Mn in indicator Mn star into X. Let me show this idea. It's kind of non-trivial. Now we plug that in there. That is the E of Mn star P is less than or equal to P into 0 to infinity x over P minus 2 to expected value of Mn in indicator then star given x. Right. We'll take P expectation outside Mn 0 to infinity, like a 0 to, let's call it Mn star from here is for P minus 2 dx. What this is on negative. Right. It's very nice, right? You get there, okay, this is equal to P upon P minus 1, expected value Mn star is equal to P minus 1. This is by respect not to get. That's the main inequality basically. So Mn star about P is equal to what is it? Now what do we do? Huh? Okay, that could be a bigger actually. You're right. Mn is just the Mn star. But that won't buy you anything. Right? Then you just figure out this thing. Yeah. So yeah, the next step is also non-trivial. Older. Who said older? Yeah, that's right. That's right. Yeah. But then you can separate these two and settle what I value you have for Mn star on that side. Because order is x, y, 1 is less than equal to basically q is equal to p upon p minus. Well, yeah. How will you get this for so if whether q is equal to p upon p minus 1. So I take x equal to mn, y equal to mn star upon p minus 1. Okay, and then we get, yeah. So I guess over here we have mn star. This I'm going to use folder on top of this of p upon p minus 1. And then so that I'm going to raise to power p. So I'll get this and then p. And that I'm going to raise to power p minus, p upon p minus 1. So I get okay. And then p. This is going to raise to power p minus 1. With this guy, I'm going to raise to power q, p upon p minus 1. I'm going to put 1 upon q outside. So once I raise to this power q, that's like raising it to power p upon p minus 1. So raising this to the power p, taking the expected value. Okay, that's what gives me m star p here. And then I'm going to raise the whole thing by 1 by q. So now I can just bring that on the side. I get myself. So up till now you're okay, right? This part is correct or?
Like I think that should be p norm of mn star to the power p,
Yeah,
p by k.
so let's see. This should be, this should be mn star. That's what it should be. Yeah, that's this threshold here. So this, but then this whole thing is raised to power
P by k.
yeah, so that's why. So this is already p at norm, so this should be this. Yes, that's right. Now it's. So get this. Now I missed one nuance here that I've assumed that mn ps norm exists, but I've not assumed that mn star ps norm exists. So one can go truncation argument to make that work. But I'll let you think about it. This is from this I've taken from Michael Steele. You can't do it, you can see. Okay, Chalo, so that's all I wanted to say about three results.
So the norm of image studies is equal to sum of the norms of k1 plus m2 plus m1. So
Yeah.
This triangle.
And then all non-negative too, yeah, even they were non-negative. So that was. So it does exist to begin with. Right. So martingales are of course used everywhere, but one interesting use you'll see if you do stochastic differential equations. See, I don't know, have you seen stochastic differential equations at all? It's like this, d of xt is some stochastic process, continuous time. It's given by a t xt dt plus dt xt d running motion here. Now, this is an intuitive notation. So there's lots that goes into showing these things. What I'm really saying is take xt minus x is equal to integral as xs ds 0 to t plus integral 0 to t bs xs dds. So then this is running motion here. So you need to define this idea of Ito's integral with respect to running motion. Huh? No, we never went around talking about Ito's integral. Could be. Yeah, that's right.
Advanced probability, the optimization.
Yeah. He went through it very quickly. But Ito's integral is a fascinating object because it differs from usual integral. Usually when I integrate with some process, it's basically this would be summation bsi xsi bsi plus 1 minus bsi limit as the interval shrinks. This would typically converge and then that would be defined as that limit. That's called Riemann-Stieltjes integral. But you run into many interesting complications when you do the Brownian motion. So, but anyway, this is not the time where I get to talk much about it. I think the point is as follows, that typically when I look at some function of t, if I look at this thing, a ti plus 1 minus a ti, for example, and if a t was a non-decreasing process, and this is, I'm looking at t is 0, 0, 0, and let's see, t. So I'm just dropping a big t into small interval, looking at this thing. Then this is a of big T minus a of 0, right? This is a non-decreasing process. And a lot of functions can be written as difference of two non-decreasing functions. These are functions of boundary variation. So then also nothing changes. You just do it separately with each one of them. So this is all that we do. With Brownian motion, you find that these things, so that's typically we talk about these kinds of, we integrate with respect to such kind of processes. Our time being a particular instance where a t is equal to t. But in Brownian motion, what you see is that, okay, and we'll probably talk a little about it later. Any t, this will actually be going to plus infinity. So this becomes a problem. Now, this, what I showed you earlier, ati plus 1 minus ati. If I were to square it, if this was well-behaved boundary variation process, then this will go to 0. Just like ti plus 1 minus ti, if I square it and sum it up, then that's going to go to 0. This is, that's maximum of ti plus 1 minus ti into big total time t, and the maximum by absolute continuity is by uniform continuity shrinking to 0 as ti plus 1 minus ti goes to 0. It's shrinking to 0 just also the way I'm defining it. So in any case, these things typically go to 0. What's nice about Brownian motion is that these things actually goes to t. But not in the almost sure sense, but in the L2 sense. So all of that makes it Brownian motion much more interesting. It's much more noisy than normal processes. So when you define integral with respect to that, you have to worry about, you have to be careful about the extra noise. That's that. But because it's very noisy and these increments of Brownian motion are independent, I don't know if I mentioned this before to you, but increments of Brownian motion are independent.
Each of this is an n 0, ti plus 1 minus ti.
What's that?
Each of these a normal 0, delta ti.
You can take out, it's distributed like that.
The ring isn't the sum just n 0, t.
Yeah. So it's n01, and then you have, okay, this has, each one of these has variance of ti plus 1 minus ti, and now you're squaring all of that. So it's normal 0, 1 square to that whole square. Right. But that converges to t. Then one can check. Right. Give me 1 second. Yeah, this is basically normal 0, 1 in times square root of ti plus 1 minus ti. That's how you get the right variance. So when you square it, you get ti plus 1 minus ti. N01 square has an expected value of 1 variance. So that comes outside. And the summation is just t. That's how you see this. But you see this in the L2 sense, not in the almost sure sense. So then, that's what makes kind of defining Ito integral that much more challenging. So there's Ito's isometric. Very nice ideas get come in here. Right. But the reason I'm mentioning all this is this is very kind of, it's a complicated definition. But and then on top of that, you're defining these stochastic differential equations. Now I have xt on this side for each t and xs there. So how does one reconcile all of these things? And the way you do this is that you first define this process x t0. Let's say straight line. You heard this? Picard iteration. Yeah. And then you put in the nth process here, and that's how you get that in this first place. is the same thing, and exhibit. So now recursively you build up this thing. And now you need to show that this, what I've constructed like this whole process is converging to something. So in converging to something, Martingale's their key. All of these dupes, inequality, LP inequality, and all that, they help you kind of show that these things are shrinking together. You wouldn't have been able to do all this without that. But Martingale's play a role everywhere. It's probably, but nonetheless, this is interesting to point out. All of this you can read up a bit on your own on this Michael Steele, if you're interested. Very good job. Okay, so now we come to L2 multiplication. That's what I mean by this. Second moment is this weekend. That's what I mean by the
Image. So this is the hypothesis. This is the hypothesis.
Yeah, that's what I mean by L2 multiplication. I'm not saying L2 bounded multiplication, I'm just saying L2 multiplication. L2 bounded would mean that all these guys are uniformly bounded. Now you see that. And what's interesting now is that now you have m of t2 minus m, let's say m of t4 minus m of t3 times m of t2 minus m of t1. But 0 less than t1 less than t2. So what can we say about this guy? Yeah. How do we show this?
These are independent variables from product.
They're not independent, right? They're marking it down.
Oh, sorry. So the condition on MT2 and MT2.
Yeah, so what, yeah, MT2 would work, I guess, yeah.
And
Although you probably should condition on
MT3.
MT3 is a better thing to condition on, yeah. Because if I condition on MT3, this is just a constant, it comes outside. And this is now a mean zero equivalent. So the expected value of the conditional expectation, that is conditional expectations. Okay, so these are basically, that's the property of Martingale's, that the increments are uncorrelated. They may not be independent, but they are uncorrelated. So what that means now is that I can write E of mn squared is equal to E of m0 squared. So I'm allowing now m0 to be random. I need not, but let's just plus summation k equal to 1 to n E of mk minus n k minus 1. So this representation is right. Basically, I write mn minus m0 as telescopic sum. Then I square both sides and cross terms vanish. So So now you can see that mn is L2 bounded if, what's the if this summation is finite. That's interesting. It just follows from this equation, if and only.
So even if is somewhat going to infinity, but it's finite and there is a upper bound. So even if this increment sum was going to infinity, we need to still know that expectation of n square is still bounded by just the first n terms and not.
No, but you want the soup. L2 bounded means that the soup will go. Soup overall. Oh, I want this to be bounded. That's why I mean that. So that boils up to this. So often this becomes a much easier condition to show than L1 boundedness. So if you show this, then this implies L2 boundedness, which implies L1 boundedness, L1 is drawn by this, which implies that Mn converges to M infinity. Very interesting fact is that although Mn converges to M infinity almost surely, it need not converge in L1 we saw when we had L1 boundedness. When you have L2 boundedness, it also converges in L2. So Mn does converge to M infinity in L2. You can see that. So we should this one. So it's going to be E of yes, Mn plus T minus square. That's equal to summation yes plus 1 and plus T. No. T plus 1. Right, I just like to say the telescopic sums squared constants vanish. Shubhanda would say we picked a lemon for a reason. Right? Because you can apply for two lemma to it. It comes inside. So you get E of M infinity minus Mn squared. That's equal to okay. And now since this is going to 0 as n goes to infinity, that tells you that M infinity is converged to Mn. Mn is going to M infinity in the L2 sense. So we see this very nicely. It's very interesting that in L1 we could not say this. In L2 you can. Okay. Again, all of these things become much more interesting in continuous time. But they're interesting enough, I guess. Just see them. When you start seeing examples, then you see a lot of uses of these things. So let me talk about Doops decomposition. And then if I run out of material, then I'll ramble about the large relation theory. That's the plan right now. So Doops decomposition is also nice. So suppose No. Actually, it's not good. Do mighty. So we are given a process xn is an adapted process. I'm ignoring underlying space filtrations, that's understood. Process in okay. Presented as zero plus mn plus an, where mn is martingale null at 0, meaning m0 is equal to 0. So m0 is 0, but it's a martingale basically. So every process has a martingale part of it, the noise part of it, and a signal part of it. That's a big idea basically. This gets used a lot in lecture engineering. And an is a non-anticipative or pre-visible process. This null at 0. A0 is equal to 0. An is fn minus 1 measure. That's what this means. Okay. But this guy was supposed to come today, right? Shantanu?
Yes.
He's arrived. Probably just setting up. Is Saurabh okay? Saurabh.
I did not see.
Yeah, Saurabh is probably just dealing with all these things. Okay, anyways, this is true, and then furthermore, if xn is equal to x0 plus n tilde n plus a tilde n, m tilde n, a tilde n are as above, meaning same property as above. Martingale and pre-visible processes, null at 0, then m equal to m tilde n, an equal to a tilde n. I'm not sure. So it's unique, this decomposition is unique. So all this you'll see in a moment, it's very kind of obvious kind of thing you're saying. It just becomes much more fascinating in continuous time. There is a deep result. It belongs to this one. If you see this right now, you'll see, okay, why make a big deal out of it?
In continuous time, what will be the difference?
What's that? It's called predictable process. It's kind of known that when you've not seen the process till time t, it's just before t you see
Yes,
it.
I mean, now we detected continuous.
The union of all sigma.
yeah.
Just.
Yes. So immeasurable is F T minus.
Isn't probably predictable?
It's also adaptive. So adaptive is measurable. It's continuous. Every continuous process is going to be predictable. Is going to be. So when every adaptive process is predictable, the other way around is inequality. I may not be, I may be on some kind of a leave next year. So I'll probably be around on the weekends and some days, but I won't be like officially. I'm saying this because otherwise I could have taught a course on continuous time probability. That could have been a way to see all these things. So maybe we can do that some other point. But nowadays, whatever you want to do, when you algorithms, complexity, information theory, all of these things, it's good to know all of these continuous time as well as discrete time. You should not have black spots in your knowledge. You only gain by knowing all these things. Okay, so how do we see this? First, let's just assume that we have such a decomposition. Okay, let's assume Xn has a decomposition. Okay. Then we have Xn minus 1. So we subtract Xn minus 1, X0 goes away. We look at this conditional expectation, Mn goes away, and that gives you An minus An, right? A0 is equal to 0, so that tells you immediately that An is equal to summation P of xk minus xk minus 1 given yes, 1 to n. So it's like at every step you say, okay, how much am I going to increase on average? And I can see xk minus 1, how much is the change going to happen on the average? Let me add all the signal up basically, expected signal. That's An, it's capturing the signal inside. And now you go back here, and now that we know An, let's find Xn, just for plugging in there, and you'll get that, okay, find Mn by plugging in there, and you get that Mn is equal to xk minus E of xk given to k. I think that should work. I'm just worried about the x0 part. Yeah, no, I think this looks correct. So you can see that at time k minus 1, you expect to see this, but you actually see this. So this is a zero mean noise that you see. So I'm summing up all the zero mean noise that I see. And that's the value. At every step, I see, okay, where am I going to go next? Let me subtract the expected value from it. Then I get the zero mean noise, let me just sum that. So that's the martingale. So every stochastic process has this martingale. But really, it's just separating signal and noise. So when you're doing stochastic gradient, you separate the noise, and you say, because I'm decreasing step size, the noise is actually going to go to 0. It's going to vanish over time. So signal is what's really remaining, and that's going to give me the right gradient to take it to the optimal solution.
Yeah, actually, is a problem getting
I went for
Instead of extend it was just given for
So it has a name. I should mention this that furthermore, and now you can see that since xn can also be written like this, it has to be unique. The decomposition has to be unique, almost surely. And because you have this, you also have one decomposition like this. Just to take your mn and add in this one. That completes it. That's what there is to this. Okay, furthermore, one more point was xn is a sub-martingale. I guess even super martingale is the same thing. If signal is increasing, yeah, exactly. So, almost sure. Everything is almost sure. So we go to some a infinity, which could be infinite also on some omega. So I think I'll just say a few things, I guess. So suppose just a couple of more things basically. Suppose M is a martingale. What can we say about Mn square? So, let's look at that. So, some martingale, right? So this is greater than equal to.
What's the N square minus the area, like n time, I mean the sum of the variances.
Yeah,
The
it's
increment is a martingale. So
Yeah,
conflict
that's it. Because of that also, yeah. You can use that argument. Because that variance is non-negative. But you can it just follows from here because now this guy here is exactly Mn minus 1. Which is the defining property, right? Mn square given Mn minus 1 getting equal to Mn minus 1 square.
Research
This Jensen's. So it's whatever I said is true for all convex functions. So all convex functions of martingales are sub-martingales. But you do need them to be, in this case, you need this to be L2. Just to define a martingale or a sub-martingale, we need that L1 property to hold. So phi of Mn should be in integrable for all things. Now we do what you were suggesting. Which is that let us write Mn square. Let's take M0 to be equal to 0. And then this is equal to Nn plus An, right? Nn is a martingale. This is overgrown. Okay. Yeah, I don't see. It's hard to find kind of books which give a lot of problem. If I was, I guess one needs a lot more time and etc. to create your own problems. So you look for books to have problems that make life easy, but it's hard to find good books to have a lot of interesting problems. I guess nobody who's working on this finds time to solve them. Okay, so why did I want to do this? Okay, so this is a martingale, this is a non-decreasing sequence, right? So then you say, okay, you have mn square is L1 is L2 bounded if, so we know this is increasing, so A infinity exists. So E of A infinity is less than infinity. So you get a very nice condition for L1 bounded. L2 bounded. All right, so good. So we are done with the whatever I want to cover with martingales today. I'll just ramble a bit about the large deviation theory. Today I'll keep it very intuitive, just to give you a intuitive flavor for how to think about things. I don't know how much you know about it already. So at the basic level in large deviation theory, we're looking at IID sums, right? So Sn is equal to, say this, all our audience in the Zoom connection and posterity. But Sn is equal to summation xi n. And second moment, that. But we know that Sn by n goes to E of x, law of large numbers. And we know that, okay, Sn by n minus E of x goes to 0, and then you multiply by square root of n. You get a non-trivial limit, divide by sigma squared is radius of x. And we know that this converges the distribution to normal 0, 1. Okay. And that's essentially telling you that Sn by n roughly looks like E of x plus sigma by root n into normal 0. Right? What that means is that we understand the deviations around the mean of the order of 1 by root n through central limit theorem. And in large deviation theory, we are asking ourselves what happens that when Sn by n is greater than equal to A, or A is greater than E of x. Right? That's a large deviation that we want to understand. It's taken a large deviation, right? It's a very unusual variable that's happening. Not explanation.
is what?
Hmm?
A
A is any number more than E of x. And I mean, whatever I say greater than equal to A also holds for less than equal to A for A less than E of x. Just take negative or excess. It is a different regime. What's nice here was that it's invariant to the distribution. The only thing that matters in that small regime is the first moment and the second moment. But this will actually depend on the complete distribution. So how do we understand this? Simplest way to understand this intuitively is first and basically what I'll talk about is I'll assume that all the xi's are light tail. So light tail means that what does light tail mean for what we know?
The probability x greater than equal to p has some upper bound.
Some exponential.
Exponential. Oh. So the homogeneous function u bar theta x is finite for theta in an open neighborhood of 0. This is open neighborhood of 0. So if this is finite in some neighborhood of 0, then you can show that the probability of x, probability of Sn by n to get equal to t is going to have an exponential bound. But it's just by Markov inequality, those kind of things. Exponentiate. So this is the light tail property, but it corresponds to t tails decaying at an exponential rate. So, but the main point is this: in this world, where xi, this essentially is telling you that xi are not very variable. Right? They are moderately variable. They're light tails. They don't have heavy tails. Heavy tails correspond to when this guy is infinite. We talked about this before. So in this world, this probability Sn by n greater than or equal to a, we'll see, roughly looks like Sn by n lying in the neighborhood a n a plus any.
So A does not depend on n. A does not depend on n.
A, I'm keeping it fixed right now. Yeah, I'm keeping it simple and fixed. I could keep allow A to depend on, but to get the story right, I think let's keep it fixed. But this is saying all the action is near A. Bigger picture is that okay, unlikely event like Sn by n getting equal to A happens in a very likely manner, which is very close to A. It won't happen, if I say, what's the chance if I roll 100 fair coins and I see 80 heads, 80 or more heads, it's very likely won't be 84 heads. It would be 80, 81 heads. That's where most of the marks will be. Very close to A point. So in the limit, all this becomes very clear. So unlikely events happen in the most likely way. Finding the most likely point becomes a convex programming problem, which has a unique optima. So in some sense, most likely path is just it's a nice optimization problem with a unique solution. So there's a lot of probabilistic structure that comes to this. That's what makes all this very elegant. So let's try to understand this probability. See, this probability is very easy to understand, as you already know. This is, let's assume there's a density function. So this is just, these are all independent, right? Sn, that is 19 n times a plus epsilon. That's what this probability is, right? So the point is, in all of this, the point is that even though this is a highly rare quantity, but you can extract determinism out of it. You can say very precise things about this. That's what it is not that ability to do these things. So how do we extract that? One thing we do is we do a change of measure. So we look at these probabilities f theta of x, which is e to the power theta x f of x. We bias them by an exponential function, higher way to larger value than theta is positive, and to normalize to make them into probability density function, we subtract just do this properly. So lambda theta is just log of homogeneous function. Log of homogeneous function. What's nice about log of homogeneous function, you can check later, or we can use it later at some point. You double differentiate it. It's also it's a convex function. So the double derivative happens to be a variance of a random variable. So it's typically a strictly convex function. Log of homogeneous function. Okay, so we have this new distribution function, and this we have as long as theta is in the neighborhood of the domain of let's go T. So whenever that's the case, I can do this chain transformation, right? I'm not worried about this guy being equal to infinity. Then I can't do all this. So once I do this, then my probability is sent by n 19 a and a plus epsilon is essentially equal to Sn by n a plus epsilon is e to the power minus theta to Sn summation x is small s. This minus, so I would have written f of x I've written as f theta equal minus theta x plus lambda plus theta xn dx. So this is called the change of measure argument. I've just re-expressed that probability under different probability measures. And essentially I've divided by a new density function of x1 to xn and multiplied by a new density function x1 to xn. More generally, it's the use of Radon-Nikodym theorem. And so this here is just the Radon-Nikodym derivative between the original density f and f theta. Probability measure of x1 to xn original and probability measure x1 to xn and the new density function. So all of these are linked together. But let's keep our discussion very simple. So the point is now this guy here, because we're looking at this tiny interval, approximately we can say that this looks a lot like e to the power minus theta into NA. Right? I can get an upper bound by putting A here, I can get a lower by putting A plus epsilon. So approximately it's this. Plus n times lambda theta into under new measure Sn is lying between Nn or Sn by n is lying between An A plus. Okay. I've just taken this guy out. So this is the whole point. There's no certainty here. This is more or less deterministic on this side. Now this is very beautiful stuff here. With this term here and this term here. And the B. So now this guy is independent of theta. Both these terms depend upon theta. Turns out that when I optimize this on theta, so I maximize this guy here, because I'm getting a bound, this is bounded between 0 and 1. So this is kind of not changing very much. But if I want to get, this will be an upper bound. That's what we do in Chernow, right? We get this upper bound here. So then we ignore this guy on this side and we just optimize this and we get the best bound. But if you look at it more, more delicately like this, when I optimize this for minimizing this, I'm actually maximizing this as well. So it so turns out, this is a calculation one can do, that if I look at soup of theta A minus lambda theta, so this is a convex function, negative is a concave function, strictly concave function, supposing a strictly concave function, there'll be a unique theta star. So let our soup, I guess let's call it theta star. It turns out that you can check that lambda prime theta star is going to be equal to A. That will be interesting, right? This one derivation. Now it turns out that mean x f theta x dx, I guess my plus infinity, is the mean under new distribution f theta. This is exactly equal to lambda prime. Right? This goes again, lambda theta is equal to, it's not that mysterious, log of integral e to the power theta x. Right? So when I differentiate this whole thing comes in the denominator, and when I differentiate this guy, I get x outside. So I get exactly this one. Okay. So the theta which maximizes this minimizes this, exactly theta which maximizes this. That's the theta star That's the lambda prime. Yeah, so this is the theta sine. At that point, the mean of each increment is equal to A. So now this is no longer a rate event. This is an event which is happening in probability half, roughly speaking. If I had chosen A minus epsilon, A plus epsilon, it's happening in probability 1. So that's the big picture. This that what this is telling you is that this event, this probability here, rough is not too far from this thing. E power minus n lambda star A, where lambda star A is defined to be supremum theta A minus lambda. This is called the large deviation rate function. We'll see this more abstractly when we discuss later. But it's a legendary differential transform of lambda. It's a convex function. It's a dual of the convex function, conjugate or legendary differential transform, same thing. So this will also be a convex function. You've seen this thing before, is that right? Have you seen the dual of a convex function? So you've not seen convex duality at all?
In the other courses, but typeface is different.
What's that?
Programming, convex programming duality.
Yeah.
That is, I think, different.
Convex programming duality. It's related, I guess. Yeah, you're right. Yeah, they are related, but they are different. That's true. But this comes up everywhere. That for a convex function, there's a dual function like this. What's nice is if I now plug in this here, I'll recover lambda theta. So to that extent, these two functions are related to each other. They are duals of each other. Yes, that's the big picture. Actually, this thing can be defined further. We'll talk about that later. But you can actually argue. This is actually result by Bahadur and Rao. These were people in ISI when they did this. Very famous. This is asymptotically 1 upon root 2 pi. And double pi at theta. Theta is at theta that we have. It's called theta A. E power minus n and stuff.
The theta is down is maximum is.
Theta is down. Theta is down that makes mean equal to A. So this is sorry, there is a root n. So it's not exactly equal to this. The error term is 1 by root n, and that's captured by this. And it's not that mysterious. If you go back and look at all these change of measure arguments, what I leave when I take this thing outside, Sn minus this thing, the increment, under new change of measure, because now under new change of measure, I'm at the, this event is no longer there, it's a mean. Then that guy, it's a sum of variables around its mean as a Gaussian distribution. You plug in a Gaussian distribution, you get this expression. That also has a very nice intuition too. You have to, the mathematics is of course more intense to show. There what we use is what are called Bayesian inequalities. Are you familiar with that term at all? Bayesian? You heard this. So this is kind of saying that, okay, central limit theorem, you get the limiting theorem, but how far are you away from central limit theorem? So Bayesian inequality is bound here. That comes with it. So you use those four to make that. But it's all this comes together very nicely. So that's the intuition right now. Actual thing is much more axiomatic and
So this one does not mean third movement doesn't.
no, well, third movement follows, right? If I assume that lambda theta is, so I assume this.
Oh.
So this setting includes the neighborhood of 0. So that all the moments are fine. Otherwise, this will not work. So the whole intuition changes when you go to extreme value setting, when you go to factorial setting. In this case, the rate event Sn by n is getting equal to A, because each increment essentially has this exponentially twisted distribution. You can show that with mean equal to it. So each increment is behaving as if it's now the mean is no longer the original mean, but it's equal to A with this exponentially twisted period. While in the heavy tail setting, Sn is going to be getting equal to n times a. This event will happen because one guy takes a long term. And all the others behave as if nothing has happened. Okay, so we'll end with this. Right now, we'll still complete, I guess, we'll do maybe 1 or 2 more lectures on martingales. And then since we start on large division theory, we'll go on to large division theory. And then we'll come back and finish off with some lectures in dominant. That's it. You've seen weak convergence, we'll do some homework problems on that. You've seen extreme value theory.
So we convergence and extreme value theory are different.
Weak convergence, I'm not thinking, just extreme value theory. Now, this is a good time that you start thinking of what you want to speak about. And hopefully it's not something you already completely know. So it should not be the favorite paper that you've already read, but something new that you want to read in probability, that you want to learn. So you pick up that paper and you present that. And just run it by me and all that. Huh? So, I mean, as such, my criteria is going to be, it should be classic that all of us should benefit from seeing you present. And of course, it should be a requisite difficulty, it need not be too hard. If you have trouble finding it, then one kind of looks for a book chapter or something. Okay, good. So at some point off class hours, we have your schedule your presentations. But I think within the next, after the exam, maybe in 4 or 5 days or so, just figure out a paper and run it by me.
How long is this course run?
I guess because we started on Jan 26th or thereabouts, right? So we probably should run to the May 11 to May 15 thereabouts in that time.
And then I can use this as one.
Yeah. When are you qualifying exams?
I mean,
Huh?
May.
May end. Qualifying exams are usually later.
No, sorry, the deadline for registering is.
That's I'm traveling at that time. ठीक है, चलो let me start. Yeah.